So let's have tomorrow's homework be due tomorrow. Okay, let's talk about these conjectures here that you're making. Did you make some? I don't know. Let's find out. I'm going to call on some people randomly, and you tell me what you think that you know. Starting with, how about Adele in the back? Did you come up with anything for A? Did you make any interesting observations? Is basically what I'm asking.
When you multiply two odd functions together, you get an even function.
That's what you think? Okay. Do you guys agree? Everyone say yeah. Okay, all right. By power of the population, we'll just declare it to be true, I guess. Right? Seems like it's true, therefore it is true. All right. Is that good enough in math? I don't know. Let's keep going. How about B? Peter J. Where are you, Peter J?
Even minus even equals even.
You think?
Yeah.
Can you get an amen?
Amen.
Yeah. All right. Maybe. We said it's even, and then this second one we think is even. Do you guys agree? Okay. Are you coming up with, by the way, as you're doing this, did you come up with some cool pictures on your calculator? Or maybe you're not using your calculator, I don't know. Oh, you don't have to use your calculator. I suggested you may, but you can also just kind of think it through, right? I think you can multiply x times x to the fourth in your head and think about what that would look like. But you might come up with some interesting pictures if you multiplied 1 over x by sine x. See what you get, right? That might be an interesting graph. Does that look like an even function to you? Yeah, I don't know, maybe, right? We're making that claim. Any complaints about A and B? You guys all agree with both those results? What about Babesh? Did you come up with anything for C? Did you get there? Did you make a conjecture?
I think that.
Say it again.
I think that if you multiply an odd, you get an odd.
You think it's an odd?
Yeah.
Okay. Which did you try any of them?
Yeah.
All right, and you guys agree on that one? Odd? On the last one? Okay. Any 10,000 foot perspective on this? Anyone want to say anything? Do you like this? Is this interesting? Does it make your brain feel good to do these problems? Huh? I made them too simple? Maybe I made them too simple. At the very least, as mathematicians, listen, you guys, I think we should be hungering, maybe, for not just empirical truth, but deductive truth. Don't we want that in our lives? Don't we want to not just be kind of sure, but absolutely beyond a shadow of a doubt sure? So let's actually prove one of these just for fun. This is just for entertainment value only, okay? Let's just do it for fun. I'm going to prove that how about the product of two odd functions is even. Are you ready? Okay, so I'm going to start by saying let f and g be, fill in the blank, be odd functions. And how about let's call this new product h of x. And let h be the product of those two functions. Now I want to consider what h of negative x is, because I'd really like to show that h of negative x equals, if I claim this is even, I'd like to show it that it equals h of x, right? If we're going to claim that the product of these is even, that h of x is even, then that's what should happen. H of negative x should equal h of x. Can we show that? H of negative x is equal to f of negative x, g of negative x. And because f and g are odd, by definition, this is negative f times negative g. Isn't that what it means to be odd? Right? Negative f of negative x is equal to negative f of x, if in fact f is odd. Same with g. And this equals f of x times g of x, which is equal to h of x. Therefore, thus, h is even, as desired, right? Did we just do it? So that's how it feels like to prove this once and for all. And I just did the product, but you can do all the other ones in almost exactly the same fashion using this proof style. Do you like it?
Sure.
I mean, you should like it because it's we've just glimpsed eternal truth, right? This is not just we've just case closed this guy, right? I hope you see that and you appreciate that. This fact is not going to be like torn down by some counterexample. We've just proven it once and for all. It's deductively certain. Like even after you die, this is still going to be true. You're not going to die? Okay. Go ahead. No. But I think you should be excited about this. Don't you feel excited about it? A little bit?
Yeah.
Shouldn't it make your brain feel happy? Okay.
And then I realized I didn't do that.
X cubed divided by cosine x.
Today we want to turn our attention to section 1.4 of the book, which deals with building functions from functions. The general idea of this is something you've thought about before, and I know that's true because in the warm-up I asked you to do it without even batting an eye if you did it. Multiplying functions, dividing functions. We'll also talk a little bit about compositions, which you know about, but we're going to shed some more depth on, some more light on these subjects I think you'll find. And we'll also talk about something I'll call implicit functions, mainly because it's just in section 1.4. I mean, not because it's like intimately connected with the other things. So here we go. Let's talk about sums and difference and products and quotients. These definitions up top should be of no surprise to you at all. Like every single one of those should be completely like exactly what you would expect. Isn't f plus g just f of x plus g of x? I mean, like I said, I barely even have to say that you knew that because you did the warm-up. The part I really want to focus on is this like domain issue down here, okay? So, in fact, there's really no algebra to do in this problem. I'll just give you the answer, but I want to think hard about the domain here. That's what I want to do. It's asking me for f minus g, right? So that's ln x minus the square root of 2 minus x, right? So, in fact, I like made it intentionally, so there's like really no simplification to even do. We're done. Okay, but now here's the big question. What's the domain of this? And maybe this is something you haven't thought a lot about before, which is why, like I said, I want to go a little deeper today, if we can. If you started doing the challenge problems, some of the first exercises in the challenge problems might have felt a little bit like this, actually. So this might, they weren't maybe as bad as this? Okay, all right. This will help you, though, maybe thinking about this. Maybe we'll go back and help you try those again. Okay, so what does this say? The thing I starred, which just kind of breezed over it. What does it say? The domain of this new function is the intersection of the domains of f and g. And by intersection, we mean like, sets. Like set theory, right? Like, we're talking about the intersection between them, not like a point of intersection. Like, we're talking about the intersection between two sets. Okay. So we need to maybe start by identifying what the domain of each of the functions f and g are. That would be a good thing to maybe start with. What's the domain? Because maybe I just assume you know what the domain of ln x is, and if you don't, maybe. What is the domain of ln x? This should be on the fifth or something. Mumble, mumble, mumble. Someone say it like they mean it. I hear some equal to's in there, but right, it's just x is greater than or equal to 0, greater than 0. So maybe we write the open interval 0 to infinity like that or something. Okay. Or we could write x is greater than, strictly greater than 0. That's the domain of ln x. What's the domain of g? Think about that one. G of x. It's a tricky one.
It's got to be
Greater than equal,
Yeah.
no, greater than.
less than or equal to 2.
Less than or equal to 2? Greater than or equal to 2?
Less than or
Between
equal
negative 2 and 2, I heard. What? It's easy to
to,
test.
no, less than or equal to 2. Less than.
All right, we'll do mathematics by consensus again. I think it's less than or equal to 2. Yeah. So that's negative infinity to negative 2, including negative 2. That means we can plug negative 2 in. Do you agree?
Yes.
Not negative 2.
Wait, it was
2.
It was positive 2. That's what we got.
There we go. All is well now.
Yeah, 2. Thank you.
Can we plug in 2? Yeah. Can we plug in 1? Yeah. Can we plug in negative 100?
Yeah.
Yeah, I think this is working. Okay, I think I'm good now. Now that we've established that, what is the domain? Let's return to the actual question we care about. What is the, what does it say? The intersection? Go ahead. Yeah, right, it's like half open interval x from 0 to 2, like that, right? From x has to be greater than 0 and less than or equal to 2. Okay, so I think we've done it. Yes? Does that make sense? This is, like I said, I think this is the element of this process that maybe you haven't thought a lot about before. Right. I know you know how to like subtract two functions, but I'd like you to think about the domain a little bit. Anything else you want to say about that? Go ahead.
What's the notation of this x something?
X is an element of this set, of this interval in this particular case, yeah.
So we can still use like greater than or.
Sure, yeah, any correct notation is fine with me. Okay, here's one for you to try. Go ahead. There's like a small thing on the previous slide that we didn't pay attention to. We'll see how well we pay attention. Just take a minute. All right, I hear some conversation. The interesting part again is maybe not the algebra here. Like, in fact, there's really no algebra to do on part A, right? We're done. I don't have anything else I want to do to it. I'm just going to leave it that way. The interesting question I want to ask is about the domain on each of these. So, what is the domain of A? Who wants that one? Want to walk into that one? Domain of A is, go ahead.
The domain of A is x is greater than 0.
Are you just?
Yeah.
Good. X is greater, or T
T, whatever,
greater-
whatever the thing is.
greater than 0. But wait a second. The domain of P is all reals, and the domain of square root of T is reals greater than or equal to 0. So isn't the intersection of that just T greater than or equal to 0? Why did you say greater than?
You can't have a square root on the bottom.
You can't have a square root on the bottom. I do, though. What do you mean?
I got rid of the
You
square
can't have a what on the?
a square root.
You can't have a square root at the bottom.
Wait, isn't that like not?
This is fine.
isn't
What do you
that-
mean? What do you mean? What say you? You can't have a 0 on the bottom, right? So, yeah, exactly. So, but you're right, absolutely. And it said that on the previous slide when we just missed that, right? The denominator of a quotient of two functions, the denominator can't ever take on the value 0. So,
Well, I just multiplied by square root.
well, knock yourself out. You don't have to do that, though. Brilliant. There we go. I challenge you, though. Have you just rationalized that expression?
Yeah.
Did you, though? What if T is equal to pi? Don't you have pi on the bottom? And isn't that irrational?
Yeah.
What now? Okay. Let's keep it's like an interesting. No, you can do whatever you want to do. All right. Okay.
What now?
Wait, what? You don't look at that.
That's true. You just got recorded. All right. Listen. All right. Let's talk about B because there's some interesting stuff to look at there. Take a look. Tell me what you see. You want to walk into this one? What's the domain? Maddie. What do you think? Yeah, and T greater than or equal to 0. Yeah, exactly. It's the intersection of the two domains. I hear some people say, wait, what? When you simplify this, you get, wait, what? What do you get when you simplify that, if you wanted to simplify it? Just T, right? So, this is interesting. Is that true? Your calculator never tells a lie. That's for sure. Ever. Never, never, never. Where's the calculator?
It doesn't lie, but it never says no.
There it is. So I've prepared my calculator ahead of time with this. The square root of negative x times the square root of negative x. Are you ready to see the picture? It better be what Maddie said, or else then we're all liars. That's a terrible picture, sorry. Wow, there it is. Y equals x, isn't it? Just like you said, except only the positive part of it. Right? I think all is right in the world again. Let's just look at the table too, just for fun. I want to see errors everywhere. That's what I want to see. Ah, there we go. Okay. Okay, cool. You like that? Try it on your own calculator if you don't believe it. Okay. Let's talk about compositions. Wait, you have a question. Go ahead.
If you put negative, instead of doing negative square root of x times negative square root of x, if you did negative square root of x squared, it comes out as only negative. Why is that?
Say that one more time.
So if you did the negative square root of x, like the parentheses thing,
Oh, okay.
you do that times that, it's positive, but if you do that squared, it's a negative. Why is that?
I think you just maybe entered it wrong. Let me see. Let's see. I think you mean, but I think maybe you didn't enter it the way I'm about to enter it. I think you mean this, right?
Maybe that's what I did.
Because I think I'm going to get the same picture. Is what I think.
But if you don't
Did you have the negative out front, maybe? Make sure the negative needs to be squared too. All right, let's talk about compositions. I know again that you know something about compositions. I assume you already know this little open circle notation.
Fog.
Maybe you've even heard fog said before. Fog and goth, right? Whatever. Okay. So by that we mean we often write that, but we often write this as well, right? F of g of x. We're taking the output from g and it goes into f. So that being said, again, I know you know what a composition is. The big emphasis here is going to be on the domain, and of course I've hand selected some problems that are just going to blow your mind. Go. Ready? Let's try this. Here we go. They look not too bad, Mr. Chase. See how this goes. Notice that the thing I'm writing here about the domain is different than the thing I said earlier about the domain. For composition, we've got a different thing happening. Just want to be real careful about this. This is my recommendation. Write it down, the domain, down, before you ever do any simplification. I think that will keep you out of the weeds, if you follow my time-tested advice. Okay, so f of g of x, right? We're doing f of g of x. So without any simplification, can we just someone write that what those things are down here? What would that be? Don't simplify it. Not even a little bit, please. How about John? Where are you? John L. John L. Right? Can you just tell me what sort, or you want to write? Okay. Like without any simplification. I forbid you from simplifying. Just what would it be?
Okay. 4.
Okay.
Times the quantity of x to the 3 over 2.
Uh-huh.
Parentheses and then squared.
Yes, that's what I wanted him to do. Do this one too while you're at it, just for fun.
Okay, and then that's x, it's parentheses and quantity of 4x squared to the 3 over 2.
Okay, that part's the part I think all of you should be able to do without any correction. Now comes the crazy part, right? We want to think about the domain, and we want to think maybe about trying to simplify these too. So talk to me. Well, I want to hear from you as you're doing it. Talk to me. What do you think? What is? I mean, you can go ahead and simplify this. I hear someone say 4x cubed is what this is. Okay.
And the domain
But when
is greater than or equal to 0.
But when it comes to naming the domain, make sure you look back at this. Okay? You want to explain?
If you look at the domain, 4x squared is all real numbers, but x to the 3 halves is x cubed, square root of x cubed, so you can't have a negative number.
Yeah, remember where you came from. I might even say, remember your roots. You know what I mean? Like this is.
You actually say that?
Yeah, right? Okay.
It's actually good.
Wasn't that good? You like that? Okay. Literally, remember where you came from. And this, what is x to the 3 halves, right? This simplification, that was your business. That's not the function I'm talking about. This function that we wrote down initially, that's the function we are talking about. We should simplify it. I think that's a matter of good taste. But when it comes to like saying what the domain is, we should say what the domain is of this thing, which is the thing I asked you about, right? And again, if you were to type this into your calculator, feel free to, you would see only positive values and 0, right? Plot it. Feel free to do it. Okay? How about the next one? We can talk to you about that one if you're ready to go there. Do you have an idea? What's going on there?
Is it all real?
The domain? Talk to me about why.
Because you're gonna square it, so if it's negative, it'll become positive.
Yeah, almost this like 4x squared kind of acts like a filter on this function 3 halves. Because I hear you say like, wait, no, that can't be right. Because we just discussed, we got this thing raised to the 3 halves power. And we just talked about the fact that stuff to the 3 halves power, you know, we can't put negative stuff in there, but that's okay. Because this won't ever be negative, will it? So I think we're okay by saying what you said, that it's all reals.
It's correct.
I think we can plug negative values into this or positive values, 0, anything. Are we having fun yet? Okay. Okay, we're not in the clear yet though. What does this simplify to?
8x.
You figured out what 4 to the 3 halves is? 8x cubed, I hear you all say?
Yes.
Okay. Wait. You have your calculator nearby? Please plot this 4x squared in parentheses to the, in parentheses, 3 halves power, and tell me what you see. I want to know whether we're right. I think you already know what 8x cubed looks like.
Ish.
Is this 8x cubed? I mean, wait a second.
The domain is right, but it's a quantity. It's not a cube.
How did this happen?
What?
Yeah, so Isabel, say it again, what you just said to me. I heard I'm not paying attention. So you're all seeing this like mind-blowing picture that this is definitely not 8x cubed. So what's happened? Tell me what you just said.
You can't have any negative numbers after you do x squared. So it's
And by what do you mean by it and have negative numbers? Say
the graph, like the function can't have any negative range numbers because
range, okay, I like that.
Okay, because you squared it, so like this part just moves up.
Yeah, we don't even need the graph to justify what she said, right? We don't even have to think about the graph. We can just look at this expression and say to ourselves, this definitely never outputs negative numbers, right? So something went wrong when we went from here to here over this equal sign. Can you help us? You think you got something, Rafi? Yeah, you could just leave it as x to the 6 over 2. That's true. That's true. You had a problem in the homework last night that asked you about this. Can you talk to me about that? What did you learn? What is that? I mean, everyone should. If you answered that question, then you know what it is. It's supposed to be. And it's not like the absolute value function. It doesn't resemble the absolute value function. It is the absolute value function, right? Like they are the same thing. This appears here, doesn't it? Do you see it? It's the square root of x squared, isn't it? And then cubed, So let's fix this. Now we're good, I think. Now we're good. What? Yeah. I think we're good for now. Try it. Kind of crazy, right? Yeah.
Wait, so for the composition, you don't have to remember the roots.
You don't have to remember what?
The roots, only the final answer matters.
No, I mean, how do we figure out the domain is all reals? By looking at this. How do we figure out the domain is greater than or equal to 0? By looking at this. So you have to remember what you started with before simplifying.
But like, it's not the intersection.
No. Exactly. No. Right. Yeah, let it be said again. It's not the intersection. of the domain. That is for sure when it comes to compositions. Okay? I think that mistake is often made, so let's say it. Okay? That only applies to the ones we were doing at the beginning of this PowerPoint. Okay, here's just kind of a curious question that I think is fun. I composed two functions. What two functions do you think I composed to get this? Like, what was the inside function? And what do you think the outside function was? The inside function, can you read my mind? Looks like I composed, the inside function looks like x plus 1. And the outside function, yeah, what you said. Okay, and then how about this one? Let's give some people some think time on this one. What's the inside function and the outside function? Don't give people some think time. And then we'll ask someone. You understand what I'm asking, right? I want you to like look at these kinds of functions and think about inside, outside. Where's Katie? Where are you, Katie? Are you Katie? Tell me what you think the inside function was and the outside function. And okay, that's cool. And know as you're thinking about it, there could be more than one answer here. It's not like I'm looking for like one. So I want other people to be on deck to give the other answer, to give another answer. There could be an infinite number of interesting answers there. Yeah.
The f of x for the outside one.
Yeah.
Then, is x, and then the inside one is then x plus the plus 1.
I think I like that. You guys agree? Okay, and then give another option, someone else. That's perfectly good. We'll take it. Box it.
f of x could have been square root x plus 1 with x plus 2.
Right? Maybe you can come up with something even more creative. I don't know. Whatever. But yeah, totally. There's not necessarily one answer on those. Okay, let's say something about this other topic called implicit functions, even though it's kind of a turn a little bit. Sorry. It's just in this section too, so we'll talk about it. It is cool. And it's fascinating. I just don't know how to like really well connect it to the stuff we've just been talking about. So sorry. Normally I like to like produce like a concerto for you, but this is not part. This is like a second movement or something. Okay, here we go. So we want to acknowledge, like straight up right now, that like there are things that are not functions that are useful to us and interesting. And you'll find that to be more and more true the more you go on in mathematics. You've already encountered things like circles, which we want to care about, but are not functions. We do care about you, circles. We maybe even care about you, whatever you are. X squared y plus y squared equals 5. Can we talk about those kinds of relations as well? Sure, we can ask questions like this, and you can answer them like you're about to do. Ready, go. Which of those points is on this curve? Who knows what it is? Is it a circle? Is it an ellipse? Is it a post? What is it? I don't know. Doesn't matter what it is, but you can answer this question, can't you? If you plug in 2 for x and negative 5 for y, does it work?
Yes, the first one.
The first one does work, people are saying? Try the others too. This one doesn't work and this one works. That's what people are saying. Just go through and confirm them. The first one works. Let's just check. 2 squared is 4 times negative 5 is negative 20.
Yes, it works.
Plus 25 is 5. So I think 2 negative 5 works. There's no way that I could expect you to graph this really, but so just know that. I'm going to show you the graph, but know that there's no way I can expect you to produce this necessarily. Are you ready? This is what this looks like. There you go.
What?
It's pretty.
Isn't it pretty?
Like,
Yeah.
it's demented.
Adele.
A mustache and a beard.
If we were ever
Or
talking
is that-
about in order to choose,
Right. Yeah. I'd have to maybe give you ordered pairs or something. You might kind of start thinking about how would I plot something like this? I mean, how did Mr. Chase even get this plot? That's a good question.
Yeah, like, where did you find that?
I mean, you could get it if you
Where did I find this? It turns out, by the way, that this is like an extremely interesting area of mathematics that's still like very open, even though it's a really simple idea. Studying curves of this type is like still a little bit of a wild land. You know, you can still go out there and do new research for sure, thinking about these curves. Even though it's pretty simple to come up with these equations. We don't know everything about them yet, especially when you add a cubed into the mix. Yeah, we know most things about stuff like this actually, but you know everything about this guy, x squared plus y squared equals 4, right? It's a circle. Can you solve for y? You'll get, I'm promising you won't get one function though, right? Because you know it doesn't pass the word blank s, but can you get 2? If you solve this for y, you can get 2. We would say those two functions, maybe we might say, are implicitly defined by this relation, right? We get kind of 2 functions out of this. If you wanted to plot the circle on your calculator, you'd have to plot both of those to get the top and the bottom half, right? Okay. And then I want to leave you with one challenge. We only have like 60 seconds left. But I want to leave you with one challenge which I'll leave unanswered, and that's this question right here. I want to get a plot. Oh, there's something coming up at the bottom. Neat. Okay. I want to get a plot of this. Okay, so I'll leave you with that challenge, and we'll talk again about it on tomorrow after the quiz. So think about it. Just write this down. Do this like on the bus with your friends and okay? Or with your enemies. That's fine too. Enemies are fine too.
I have absolutely no clue what it would look like. But it's going to be